My name is Flash Isaac, and I'm a teacher from the future. We shall be looking at gravitational field. Gravitational field is a phenomenon used to explain the influence of a massive object on other bodies or on the space. Every massive object exhibits or exercises certain influence, and field or gravitational field is a region where gravitational force is experienced. If I say boy, boy, those around me will hear the word. The more you move further from me, the less you hear what I'm saying. You move to a point where you no longer hear what I'm saying. In that case, you are outside my field. So the region where people can hear me, I can say that is field. So using that explanation, gravitational field is the region where gravitational force is experienced. And to explain gravitational field, we look at Newton's law of universal gravitation. Newton's law of universal gravitation states that if you have two objects, let's call this object A or body A, let's call this body B. Body A will definitely have mass. So let's call the mass M. Mass is the quantity of matter a body possesses. And when gravity acts on mass, it becomes weight. So gravity affects weight, but mass remains anywhere you go. This body B will also have mass. Let's call it small m. Since this one is here and this is here, there will definitely be a distance of separation. Let's call this distance of separation r. You can also represent it as small r or d. It speaks of distance. Newton said that the force of attraction between this object and this object is directly proportional to the product of their masses and inversely proportional to the square of their distance apart. Mathematically, this force is proportional to this m, big M. The mass of this is small m over the square of their distance. You can as well represent this mass as m1 and this as m2. It all depends on what you want. This is Newton's law of universal gravitation. Now, in mathematics and in variation or in physics, we don't solve with proportionality sign. We change to equal to. By the time you introduce equality, you get a constant. So therefore, this is equals k. The constant is g. This is g m over r square. The universal gravitational constant, big G, is the gravitational force acting on objects of unit mass kept at distance apart. That is universal gravitational constant. So big G is equals F r squared over m and m. Since this is a constant, it has its own value. The value for the universal gravitational constant is simply 6.67 times 10 to the power of minus 11 meter cube per kilogram per second squared, or 6.67 times 10 to the power of minus 11 Newton meter squared per kilogram squared. This is the value of the universal gravitation constant. And gravitational potential is the work done when you take an object from one point to another or from one point to infinity. That is universal gravitation. That is gravitational potential. And gravitational potential energy is the energy possessed by a body as a result of its position in the gravitational field. Mechanical energy is energy due to position and energy due to motion. Energy you possess due to position is potential energy, mgh. And energy you possess due to motion is kinetic energy, ke, and that is half mv squared. Now, gravitational potential is that potential energy as a result of position in the gravitational field. And gravitational field can be conservative or non-conservative. Conservative field is the field that is independent of the path. Then the energy is conserved, or kinetic and potential energy, they are conserved. Examples of conservative gravitational fields are gravity and electric field. And they don't depend on path, whether the path is rough or smooth. No. Why conservative, non-conservative fields, they depend on path and they are dissipative, which means there is loss of energy. In non-conservative field, it is dissipative, which means work done is accompanied by heat or temperature rise. Examples are friction and viscosity, where here it is not accompanied by heat or temperature rise. Now let's look at the relationship between acceleration due to gravity and universal gravitation. This is very, very important. F is equals gmm over r squared. And we know that force is also equals mg for motion under gravity. If force is gmm over r squared and force is also equals mg, it therefore means that force is equal to force and gmm over r squared is equals mg, which means mg is equals gmm over r squared. So let's believe that this mass and one of the masses are the same. If that is true, this mass cancels this mass. Therefore, acceleration due to gravity is equals universal gravitational constant times m over r squared. Take note of that relationship between G and big G. Now, there is something referred to as escape velocity. Escape velocity. We know that field is a region where a force is being experienced. Now, if this is planet A, in this planet A, we have force exerted on all objects in this planet. If you decide to shoot an object, you decide to take an object from planet A to planet B, it simply means that you need a velocity that will be able to overcome the influence of gravity of this earth. That is the only thing that will make it to escape. Therefore, the escape velocity is the minimum velocity required by an object to escape the gravitational influence or to live here. It's work done in taking a unit mass from a position to infinity. The object is trying to escape gravitational force, which means the escape velocity is work done. And the work done must be equals kinetic energy. What is work done? Work done is equals force times distance, r, or you use d, and kinetic energy, Ke, is equals half mv squared. But this velocity here is no longer the normal velocity. It's the escape velocity, because we need a minimum velocity to overcome the gravitational forces to escape to another planet. If the work done is equals kinetic energy, it means that force times distance, let's use d in this case, or let's use r, it represents distance. This is equals half mve squared. So let's look at what is force. We've been told that force is gmm over r squared. So gm small m over r squared times distance. This is force and this is distance. Everything is equals 1 over 2 mve squared. From here, there is arrow square here, there is arrow here. So one of this arrow can cancel one of this arrow, leaving behind gmm over r is equals half mve squared. We have one small m here and we have one small m here. They cancel. what are we left with? We are left with G M, big M, over R is equals 1 over 2 VE squared. If you cross multiply, you will simply have 2GM over R to be equals VE squared. And what will VE be? Square root of both sides. So escape velocity is equals 2GM over R. Where is it? Escape velocity is equals 2GM over R. But look at something. Look at something. Be very, very careful. G is equals GM over R squared. Multiplying both sides by R, G times R is equals R times GM over R squared. This R, we cancel one of this R. G times R will be GR. GR is therefore equals GM over R. Why did I do this? Since GM over R is equals GR, escape velocity VE can also be square root of 2GR, because GR is the same thing as GM over R. These are therefore the two formulas for escape velocity. And looking at acceleration due to gravity, small g, it varies on the Earth's surface. It depends on the shape of the Earth, and it depends on the rotation of the Earth. It also depends on altitude. So G is higher at the pole than other parts of the Earth, because the pole is closer to the center. So G depends on shape on the Earth. It also depends on rotation of the Earth. Acceleration is due to gravity increases with latitude because of the centripetal force, and also it decreases with height or with altitude. G is inversely proportional to H. Up next, parking orbit and weightlessness. In the last two episodes, or in the previous episode, we are solving a question on elevator, and we said that elevator going down, the person will feel weightless because the weight is more than the reaction. In fact, there is no reaction. When there is no reaction, a body will feel weightless. So weightlessness occurs when there is no reaction, or when the net force acting on the object is zero, or when acceleration, linear acceleration, is equals acceleration due to gravity. That will give you weightlessness. And what is parking orbit? Parking orbit is a curved path of an object in the plane of the equator. Curved path of an object in the plane of the equator. Examples of parking orbit are relay satellite in TV and surveillance satellite used for spying. These are examples of parking orbit. Ladies and gentlemen, just in few minutes, I've been able to explain everything about gravitational field. And this is something that would have taken you 2 weeks, 3 weeks to learn if you are reading on textbook or you are attending classes from gravitational field. Look at this first question here. We are given the value of G, we are given mass of Earth, and we are given the radius of the Earth. We are also given small g on Earth. We are looking for the Earth's gravitational field intensity. Anytime you are asked to look for the Earth's gravitational field intensity, the Earth's gravitational field intensity is equals force per unit mass. So it is force over mass. And what is force? Force is G M M over R squared, or D squared, and mass is M. What this will achieve is that G M M over R squared divided by M is the same thing as times 1 over M. In other words, M here will cancel this M to give you E is equals G M over R squared. This is the formula we need. If you are not using R for your distance, you can say GM over D squared if you are using D as distance. Up next is for you to substitute the values. If you put G as 6.7 times 10 raised to the power of minus 11, then you put M to be 6 times 10 raised to the power of 24, that is mass of the earth. Then the distance 6.4 times 10 to the power of 6. But this distance or radius is squared. Radius of the earth is the distance of separation. Doing that, your answer should be 9.8 Newton per kilogram. And mind you, we are not making use of the small g. It is not necessary in this question. So option D is the correct option. Work done on an object to bring it to a certain point in space is called gravitational potential energy. Gravitational potential energy. Work done on an object to bring it to a certain point in space. And remember, it is the energy an object possesses because of its position in a gravitational field. Calculate the escape velocity of a satellite launched from the Earth's surface if the radius of the Earth is 6.4 times 10 to the power of 6 meters and g is 10 meters per second. We are just given g and radius. So from VE is equals the square root of 2gr. Escape velocity becomes 2 times 10 times radius 6.4 times 10 to the power of 6 meter. 6.4 times 10 to the power of 6 meter. This is equals 20 times 6.4 times 10 to the power of 6. So if you multiply 20 times 6.4 times 10 to the power of 6, you should get your answer. 10 to the power of 6 is simply 1 million. 20 times 6.4 is 128. The square root of 128 is 11.3. 11.3 times 10 to the power of 6 is 1 million. The square root of 1 million is 1,000. 1,000 times 1,000, that is 1 million. So 1,000. So this is equals 11,300. 11.3 times 1,000. You shift this 3 times to give you 11,300. That is 11.3 kilometer per second. Now let's assume we don't have calculator, but you know that 20 times 11, 20 times 6.4 is 128. You ask yourself, looking at the options, A, 4 times 4, 16. 11 times 11 is 121, which is very, very close to 128. So 11 is what will be the answer, because everything here is zeros. You have 1 and some zeros. So you use that idea to answer questions without calculator, even in. Now, studying gravitational field, it is imperative that you understand or you know the Kepler's 3 laws. Kepler's first law states that planets describe eclipse of the sun as one focus. Planets describe eclipse of the sun as one focus. Kepler's second law states that the line joining the sun and the planets sweep out equal area in equal time. The line joining the sun and the planets sweep out equal area in equal time. And Kepler's third law states that the squares of the period of rotation of revolution of the planets are proportional to the cube of the mean distance from the sun, which means the square of the period of the revolution of the planets are proportional to the cube of their mean distance from the sun. Cube is different from cube root and square is different from square root. Now look at this option. Roman figure 1. The escape velocity of an object from the gravitational field of a planet 1 increases with the mass of the object. 2 increases with the mass of the planet. 3 is smaller on the moon than on the earth. Option 2 and 3 are correct. The gravitational field of a planet, the escape velocity, increases with the mass of the planet. You see, it is proportional to mass. As mass increases, escape velocity increases. And it is inversely proportional to distance. It's smaller on the moon than on the earth. Escape velocity is also directly proportional to gravity. Gravity on the earth is bigger than gravity on the moon. Therefore, the escape velocity on the moon will be smaller than the escape velocity on the earth. Two spheres of masses 5 kg and 10 kg are 0.3 meter apart. Calculate the force of attraction between them, giving big G to be 6.67 times 10 raised to the power of minus 11. We know that F is equals G M M over r squared, or Gm1 m2 over r squared. G is 6.67 times 10 raised to the power of minus 11. M, the first mass is 5 kg and the second mass is 10 kg. The distance of separation between them is 0.3. An object of weight 80 kg on Earth is taken to the planet or to a planet where acceleration due to gravity is 1/3 of the Earth's value. Weight is not kilogram, which means this is the mass of the object on Earth to be 80 kg. The gravity on Earth is 10 meters per second square. 10 meters per second square. Now, this object is taken to a planet. Let's this be gravity on Earth. In this planet, the acceleration due to gravity is equals 1/3 of acceleration due to gravity on Earth, which is simply 1/3 times 10. That is 10/3. This is gravity on the new planet. Now we are asked for the weight of the object on the new planet. Weight is mass times gravity. Weight on the new planet is mass times gravity on the planet. Mass doesn't change, only weight does. Since mass remains constant, the weight will be mass remaining 80 times acceleration due to gravity is 10/3 on that planet, and that is 800/3. Is that 267 Newton approximately? Yes, that is it. A force of 200 Newton, F is equals 200 Newton, acts between two objects at a certain distance apart. The value of the force when the distance is halved is dash. F is Gm1 m2 over d squared. Now, distance is halved. D is now 1/2d. D squared is now d/2 squared, which is d²/4. This is the new distance. So how do you answer questions like this? Since force is proportional to distance, F(d²) equals F, the new distance is now d²/4. So what are we asked to look for? We are asked to look for the new force. This is F1 and this is F2. F1 is 200, so 200 d² is equals F2/4 d². D² cancels d². So the second force will be 4 times 200. That is equals 800. So 800 is the correct option. Now, when a brick is taken from the Earth's surface to the moon, its mass remains constant. Mass doesn't change, only weight changes with gravity. And ladies and gentlemen, an object is weighed different at different locations because the mass is constant while the weight will vary. A rocket is fired from the Earth's surface to a distant planet. By Newton's law of universal gravitation, the force will increase as radius reduce. Yes, force is directly proportional to mass. As mass increase, force will increase. As distance reduce, force will increase because distance and force are inverse. Big G is constant, so you cannot increase big G or reduce big G. So ladies and gentlemen, virtually the first questions you'll be seeing are under the formulas and the explanations we've given. The law that explains the path of motion of the earth about the sun in an elliptical manner was stated by Kepler. Thanks for watching your one and only teacher from the future. I hope you found this class interesting. Feel free to check out the playlist for more amazing videos, and don't fail to install the Flash Learners application right now for notes, videos and questions to meet all your needs. Subscribe to this channel so you don't miss out any of my sweet videos. See you in the next episode. Don't forget to tell everyone around about the Flash Learners. Bye.